Okay. Okay. Hi everyone. Welcome to the ZX seminar. Today we have Zipeng Wu from the Hong Kong University, who is going to be talking to us about ZX calculus approach to concatenated graph codes. Please take it away.
Thanks for your introduction. This is Zipeng, and today I'm happy to give this talk about our recent work, the calculus approach to concatenated graph codes. This is joint work with Chen Song and Zheng Bei. Okay, so I'm kind of like going to give a little bit motivation of why we apply the ZS calculus in this kind of problem. Graphcode is a subclass of stabilizer code. It utilizes graph states and classical words to protect the quantum informations. The graph structure provides an intuitive way to visualize the quantum state and its interactions. So prior to our work, Becky developed a method to use algebra method to concatenate the graph codes. They systematically developed a method to concatenate a outer graph code A to a inner graph code B. The concatenated graph code remains a graph code, and the graph can be transformed between the inner code and outer code utilizing a rule called the generalized local compilation rule. However, their approach is restricted to the algebra method, and the basis of concatenation is selected by the Pauli X, so it cannot be generalized to other bases under the concatenation. And another work bring this idea to us is that recently a group used the graph codes to construct the holographic code. They use the pentagon graph and use to perform some kinds of tensor network construction. Use small pentagon as a tensor network and contract the tensor network to build a larger code from the smaller one. This kind of generalize the idea of graphical concatenation, but no known result can be applied to this problem, especially in a graphical way. So we looked into the ZS calculus. It turns out that ZS calculus is very generic to this problem. The encoding circuit of the graph code can be readily transformed into the ZS encoder diagram. And since the encoding process is all Clifford, the interior nodes induced during the concatenation can be fully removed with the simplification procedure, including the local complementation and the pivoting. So we derived the ZS calculus encoder diagram for the graph code, or more generally, we extend it to the stabilizer codes. And using this encoder framework, we are able to build any larger stabilizer code by stacking the encoder of the smaller code. All right, so this kind of some introduction preliminary. NKD stabilizer code encode K logical qubits into N physical qubits with distance D. So the stabilizer code is defined by the stabilizer group. It's a subgroup of Pauli group, and which does not contain the minus identity. The the quantum state in the stabilizer code is the +1 eigenstate of the stabilizer operators. And the graph state is a N0D stabilizer codes. It's defined by a graph. So the stabilizer generator of this group is some Pauli X operator and some Pauli Z operator, which is the neighbor of I. So a general graphcode encode a capital K dimensional cumulative space into a 2 to the n dimensional space. Use a graph and a code word C. The code word C is linear. So to briefly point out that the code space will be spanned by this capital K states, which kinds of like the graph state and some Pauli Z string acting on this graph states. As I have mentioned before, this kind of state is still a stabilized state. It's local Clifford equivalent to a stabilizer codes. So we'll see a very simple example. The 513 codes. It is the smallest quantum codes with distance 3. It's local Clifford equivalent to this graph code. The graph is a ring graph with 5 nodes, and the classical code words is the C0000 and C1111. So first, it's kind of immediate to see that the code space is orthogonal. As the Pauli Z operator acting on the graph state is commutes with the control Z operator, and then we perform the conjugation of the Hadamard. It turns out it's the SK acting on the computational basis. Therefore, different Pauli Z alpha acting on the graph state will result a orthogonal states. So let's consider how a single qubit arrow acting on this kind of graph codes. As you can see over here, suppose I have a single Pauli X arrow acting on this graph code. This graph code, we will use the graph state first. The graph state actually is stabilized by the XZ, right? So if we X the Pauli X on it, it's actually, we can first apply the stabilizer XZ on it, and these two pair of X will cancel as kind of like moving the Pauli Z arrow to the neighbor of these nodes. So in terms of the ZS calculus diagram, we have a graph states. More generally speaking, the alpha can be pi because we are acting the coverts on it, and the Pauli X arrow will just pass through these nodes, and it turns out to be Z arrow on the neighbors of these nodes. So in a more general setting, we are focusing on, we can face the multi-qubit arrow. So this kind of arrow can just by iteratively applying the same procedure. Suppose 2 arrow is acting on this, we apply the Pauli X transformation, and the resulting arrow will always be a Pauli Z arrow. And the bit string of this Pauli Z arrow can be defined by this equation. So to see the arrow crafting ability of this graph code, you can kind of like imagine this graph code is really related to the classical code. The Pauli Z arrow acting on this graph code will be equivalent to the like some bit string acting on the classical code words. For the Pauli Z, it would be something like this for Pauli X and Pauli Y. So our code words is indeed able to correct the single qubit arrows, because any pair of this adding together will not flip the logical state from 0 to 1. This is kind of completely forced into the classical arrow correcting region. So I guess I'll give a little bit talk about the graph-like diagram. So the graph-like diagram is a very powerful approach for the simplification of the ZS diagrams. Basically, it converts all the X spider into the Z spider, replaced by the Hadamard edge. So if there's the diagram will be remaining with the Z spider and Hadamards. So if there's a solid line between the Z spider, they can be fused together, and when the fusing properly will induce the Hadamard loop, and it will result in a pi phase over the Z spiders. And any pair of the Hadamard between a pair of Z spiders will be detached. So graph state is kind of like a special case of the graph-like diagram. It has no inputs, and all phase are zero, and each node has connect to a unique output. So convert a classical graph into a graph state in this calculus is straightforward. We replace the nodes with the Z spider and connect the nodes with the Hadamard edge and add a output for each node. So with this graph-like diagrams, the previous work provide a very helpful simplification procedures for the graph-like diagrams. It basically involves use two lemma. One is the local complementation, one is the pivoting rule. So for a graph-like ZX diagram, it includes the boundary nodes and the interior nodes. The local complementation rule can remove the interior node with the phase as plus and minus pi over 2. And the pivoting rule can remove the pair of the Z spider with the phase as a multiple of pi. So this is kind of a generalization of the pivoting rule when a single node with a phase as a multiple of pi also can be treated as an interior node and use pivot rule to remove it. So for the Clifford circuit, using this simplification procedure, we can generally remove all the interior node and resulting a graph-like diagram with only boundary nodes. Okay, so I will talk about the encoding procedure of the graph code. As I have mentioned above, the graph code is defined by a graph and a classical code word C. The code word C is linear, therefore the capital K element of the linear code can be expressed by the small k linear basis. The K equals to log 2 capital K. Therefore, we can kind of define the logical state for this graph code, where the logical state is just the summation of the code word basis with the indices, with the computational basis, and sum over it, and resulting a Pauli Z operator acting on the graph space. So the encoding procedure of this kind of graph code can be drawn with these figures. So if you have n plus k qubits, the first k qubit is the kind of information we want to encode. And this is the n qubit using to prepare the graph state. So this part of circuit is used to prepare the graph state. And we apply the CZ gate between the top k qubit and the last n qubit according to the value of the alpha. If the alpha ij equals to 1, we'll apply a CZ between the i's qubit in the top k and the j's qubit of the last n. And after that, we will apply the Hadamard transform on the top k qubit. So prior to the measurement, the resulting quantum state looks like this. And then we perform the measurement on the top k qubits, and we suppose select the result for the all zero measurement. As you can see, it's basically set this value to 1, and it will turn the quantum state of the last n qubit into the encoded version of the input state. Okay.
Sorry, can I ask, what do you do when you get the wrong measurement outcomes?
We discard the results.
You discard the results.
Yeah.
Okay, but then if it's if k is large, then
Yeah,
you require many
it's
tries.
another way to actually this is not the unique way to perform encoding. The generic way is actually perform some control Z operation after the Hadamard, where we will cancel out this kind of phase, and resulting the top k into a superposition state. But it turns out that we kind of cannot simplify this kind of encoding diagram into a simple ZS encoded diagram, and this kind of approach is can be more easily converted to the ZS encoder diagram. So we take this approach for the proof.
Okay.
Okay. So
Can I ask, how are the code words actually defined? Are they, do you choose, can you make a choice of what code words you want, or?
yes, actually that's true. That's what I'm going to say about in the next slides. This circuit actually kind of fixed. Your input IK will map to the logical IK, which the IK is defined by this equation. But generally speaking, the code space is kind of spanned by this code states. To perform this kind of basic change, we actually perform some operation prior to the encoding procedure. One commonly used operation prior to encoding is the Hadamard operation. It basically converts the 0 state into the 1 state, 0 state to the plus state. Therefore, you kind of can imagine that it encode the plus state to the logical 0 state that we defined before. Or you can imagine that it maps the 0 state to the plus logical state, as we defined before. So to tune the logical state, we can kind of use the Clifford operation prior to the encoding procedure. But normally they choose the CL either equals to the identity or use the Hadamard, because in this choice, the logical state is easy to read, write, and the logical operation can be easily derived. So, okay, this slide just tells about how to convert the encoding of the graph codes into a ZS calculus diagram. We start with the quantum circuit, and as you can see over here, this part of the circuit is preparing the graph state. So this kind of G is a graph state with an outputs over here, and when we are post-selecting the 0 is equivalent to using the X spider with the Hadamard gates. Then it interchanges the color into the white nodes, and we are connecting the top K qubit with the last G qubit according to the code word alpha. Therefore, there will be some Hadamard edge between the top K qubit and the last M qubit, and we can readily move this Z spider within the Z spider in the graph state, and kind of turn it into this ZX encoder diagram. There's NK white nodes, K Z spiders over here, and N Z spiders over here. The N Z spider form a graph state, and the top K spider connects it to the N Z spider according to the classical codes. Or more specifically, the adjacency matrix between the first K qubits and first K nodes and last N nodes is by stacking the classical codes, the alpha 1 to alpha K. So we'll see a very simple example for this kind of transformation. So consider a graph code 311 graph code. The associated graph is a triangle. The code words is 000 and 111. The basis of this code word should be the 111. So the encoding circuit can be readily transformed into this JS encoder diagram. And this encoder is mathematically can be written as this, which encode the 0 state into the graph state, triangle graph state, and the 1 is encoded into the ZZ acting on the graph state. Okay, so this kind of diagram can be readily generalized to arbitrary stabilizer code. So consider stabilizer code, MKD stabilizer code. Its stabilizer generator is has n minus k elements. we mean encoder. Actually, we already fixed the input and the logical states. Therefore, the logical operator is also fixed. So the encoding circuit is can be written in this linear operator. It encodes the computational basis into the logical space. And from the channel state duality, this kind of linear operator is isomorphic to a quantum state. And this quantum state actually is a m plus k 0d stabilizer state. The stabilizer generator is written in this. So basically, it's the original generator tensors the identity of the last k qubits, and the logical operator tensor the Pauli X operator on the original qubits, and the Pauli Z and the original Z. There will be a minus k plus k plus k. So there's m plus k independent generators. Therefore, the encoding states. The encoder of the stabilizer code is isomorphic to a stabilizer state, and a stabilizer state is local Clifford equivalent to a graph state. Therefore, the encoder of the stabilizer code can be first expressed in this graph-like form, and we tune the channel state duality. We kind of like turn some outputs as inputs, and the resulting a encoder form, where we now apply some local Clifford operation and some pair of Pauli Z. This is also Clifford. So now the code space of this kind of encoder is just the LC. LC is the tensor product of all this local Clifford operator, and the code space now is the LC acting on the original code space, where we have a graph and some classical code words. So I will use Sting code as a very simple example here. The Sting code, the encoding circuit can be readily transformed into the JS encoder diagram form, where we have 1 qubit encoded into 7 qubits into 7 qubits, and this graph actually is used for the, as we will see later, for the concatenation for the Sting code. Nonetheless, this slide just to point out that the stabilizer encoder can be also transformed into the JX encoder diagram. So with this encoder diagram enhanced, we are now ready to use it for the code concatenation. So concatenation is kind of an idea that we have an outer code and an inner code. The quantum information is first used the first encoder, the outer code encoder, encode to a larger code space, and each qubit in the code space is used as the input for the inner code. For n prime, k prime, d prime outer code and nkd inner code, the concatenated code would be a n prime n and k prime and delta q concatenate code. The code distance will be at least d times d prime. So concatenation of codes is a nice way to achieve some codes with large distance. And according to the threshold theorem, it's also critical for the for torrent implementation of quantum algorithms. So here's a circuit example for the concatenation of the graph code. As you can see over here, we first encode this qubit into the 311 code using this part of the circuit. Then the output of this encoder is connected to the encoder of this inner code. Each of the output of the outer code is connected to the encoder of the inner code. So this kind of structure can easily transform into the JS encoder diagram. We simply connect the output nodes of the encoder to the input nodes of the inner code. So prior to our work, it was the backend work. They developed a method to describe the concatenation of a graph code. Basically, suppose you have an outer code and an inner code. The inner code has to be concatenated according to the Pauli X basis, which means that the CL that we choose has to be the hardmark. And after this setting, the resulting concatenated code will remain a graph code. And the graph of the concatenated code will be the generalized local complementation of the original graph of the outer code and the inner codes. So for the generalized local complementation, it's kind of straightforward by this diagram. We have two cluster of nodes over here, and there may exist some edge between these two clusters. The generalized local complementation is that the edge between these two clusters is the complementation of the original edge. The reason that it's generalized is that it's kind of generalized to the local complementation, which only works on some single nodes or against a clusters. So with this setting, we are now ready to use the JS calculus diagram to kind of reprove this results given by then. Consider an outer code and an inner code. The output nodes of the outer code is connected to the input code of the inner code with the hardmark edge. So we basically apply the pivot rule between I and J. This is just immediately give the local complementation between Mi and Nj. And this is for the single qubit case. And in a more general setting, the multiple inputs can be concatenated to the multiple qubit of the outer code can be concatenated to the inner codes, and the output qubit of the outer codes may exist a hardmark edge between them. So we first perform the pivot rule between U and EU. This is exactly the generalized local complementation between neighbor of U and neighbor of EU. Now we will connect it to the neighbor of EU. After this setting, we will perform the generalized local complementation between V and EV. Since the MEU and MEV is disjoint, this is exactly the local complementation for the second pairs of nodes. So it can be readily generalized to the case where multiple qubit is concatenated as long as the neighbor of EU and EV is disjoint. We sequentially just applying the pivot rule, which is kind of equivalent to the generalized local complementation rule. But there are also cases where the generalized local complementation rule fails. That's when the neighbor of EU and neighbor of EV is not disjoint. As you can see over here, we first also perform the pivoting rule between U and the EV. This will result in a complementation between MU and MEV, U and MEU. And now since MEU and MEV is not disjoint, the V will connect to their intersect. Therefore, for the generalized local complementation, we require MI and NJ is disjoint. But now it's kind of like there's some nodes which is the neighbor of MI and MJ at the same time. That's when the generalized local complementation rule fails, and we will have to use the JS calculus, the pivot rule, and resulting this diagram. So kind of final remark is that the neighbor of MEU and MEV will gain a pi phase, which is a Pauli X on this qubit, and the resulting code is no longer a graph code, but still local Clifford to equivalent to the graph code. So I use this example is kind of like to re-improve the result and generalize the result of baggage results. JS calculus encoder diagram can be readily implemented to more general setting where the Clifford operation can be extended to other bases, and the algebra method is kind of limited compared to the diagram method. The diagram structure cannot be easily visualized without this kind of JS calculus diagram. Okay, so beyond the code concatenation, there's another way to build a larger stabilizer code from a smaller one. This is done by fusing the stabilizer states. This kind of idea is that suppose I have a stabilizer A, state A, and a stabilizer state B. We want to fuse the qubits I in A and I prime in B. The procedure is kind of like we perform the measurement of the XX and ZZ operator on these two qubits and post-selecting the +1 result. Then the resulting state is still a stabilizer state. And these two qubits will project into the Bell states. So according to the textbook knowledge of the stabilizer generator, we can update the stabilizer generator table according to this kind of measurement. And this is kind of the way of building up the large stabilizer code from smaller one, and that's kind of how they do it using the tensor network representation when building larger tensor network stabilizer codes. So for the tensor network stabilizer codes, it uses a tensor network to represent the stabilizer. You can either imagine the TL is a rank n tensor or rank n+1 tensor. The logical operation L is kind of another degree of freedom. So if a operator is in the stabilizer group, the corresponding entry of the tensor it will be 1. So it's kind of very sparse encoding of the stabilizer states. When you contracting to tensor network stabilizer, it actually is the same to the previous discussion. You are measuring the corresponding edge into the XX and ZZ operator and post-select the +1 results. You are it's kind of like project these two qubits into the Bell states. So this kind of fusing is can be readily understand in the JS encoder diagram. So the projection into the I prime. So as shown in this figure, we are kind of like fusing the node I and I prime of these two encoder. We first perform the channel state duality. We convert input to the output. Now these two are two stabilizer states. Then we project the specific qubit, the I and I prime, into the Bell state, which is represented by this cap. And we turn the output back to the input, and this kind of fusing is accomplished. The last step is we want to remove this kind of imperial node into a this like imperial node freed diagram, because under this diagram we are now ready to give the explicit form of all the stabilizer of this new encoder.
May I ask, after you get this constructed diagram on the constructed diagrams on the right, do you know how to physically implement the logical X and Z for this new concatenated code?
Yeah. As long as there's no this kind of like the first ongoing things we are doing, as long as there's no control Z between these two encoded or the input nodes of the encoder, we just kind of discard this local Clifford operation because it does not affect the code space. And once we have done that, the situation turns back into the standard encoding of the graph codes, where we just maps the computational basis to the graph state with the acting on it, and the logical operation of this kind of graph code is well started. But for a more general Clifford between a input qubit, kind of don't know how to get the logical operation in the code space. And we think there are some equivalent encoder diagram where we can remove the Z or the Hadamard edge between the input nodes, and the graph would be kind of changed.
Thank you.
Okay, so
just a different question as well. I'm trying to see which rewrite you did to go from the second to last diagram to the last one. I think it's a spider fusion followed by a pivot, where you first fuse these I and I prime, and then you do a pivot with that spider and the top wire of the bottom part, I guess.
I guess it's this one because it turned.
Because that's mine.
Yeah.
I see. Okay. Yeah.
So one application of this kind of encoder concatenation, or we may call it fusing, is that to build the holographic code. Holographic code use the like the 513 code, stabilizer code as a building block. It is concatenated or the fusing into another layer of the 513 code. Therefore, you can kind of like this red node is the bulk and the yellow node is the boundary. The quantum information in the bulk is encoded into the boundary, and it's kind of the idea of the holographic code. Prior to this work, they performed the construction of this holographic code through the tensor network contraction I mentioned before. And as you can notice over here, as you extend your boundary to a next layer, the contraction complexity will significantly increase. It will become invisible very soon. So recently, the paper published by arXiv by Monet is that they used the Pentagon encoding to construct the holographic code in a very toy model using only 4 Pentagon encoder. They are performing the tensor network contraction between this encoder, and they result in a tensor network, stabilizer tensor network, and they kind of get the tabular form of the stabilizer state. Then they perform the local Clifford optimization for the stabilizer tabular, and resulting a highly symmetry graph codes. Actually, this kind of operation can be readily implemented using the encoder diagrams. So we basically rewrite what they do. We use 4 Pentagon and express the Pentagon as the DS encoder form, and we connect or fusing the specific nodes according to their setting, and we perform this kind of, first we fuse this alpha alpha prime, gamma gamma prime, delta delta prime, and beta beta prime. then we kind of symmetrically select some boundary node to perform the pivoting, and the resulting encoder diagram would be highly symmetric. And this is the resulting encoding diagram, which is local equivalent to their results. Compared to tensor network results, this approach kind of like takes no times. Simply remove for interior nodes. It's kind of fast compared to their approach, and we don't need to perform the local complementation optimization when we transform a stabilizer code into a graph code. So once this kind of encoder diagram given, we just kind of remove this local Clifford operators, and then this kind of Z-gate in the input nodes can also be removed because it does not affect the code space. So in the standard form, the control Z, the logical operator is well studied. So this kind of is the conclusion for this work. We use a graphical approach, especially the JS encoder diagram, to analyze the graph code, or more generally, stabilizer code. And this diagram is efficient for constructing larger stabilizer code from the smaller one. And the future research direction could be like, first is exploring the concatenated stabilizer codes. We didn't find much interesting example using the JS encoder diagram for the stabilizer code. And just as you can see in the holographic code results, the symmetry is kind of important in this kind of code simplification procedure. For the removal of the interior point, there are actually several degrees of freedom when we choosing the boundary node and to perform the pivot route. Some symmetry preserve operation might be preferred to when we perform this kind of simplification for the for some code. So this kind of approach may bring up some connection between different quantum error creating codes. So this kind of my talk. And thank you for your time.
All right, Zipeng, thank you very much for your talk. Everyone can applaud in whatever way you want on the Zoom meeting, use the controls or something. All right, we have time for a question. Oh, yeah.
Yes,
we have time for questions. I see Sarah has her hand raised. Alex, I know you also unmuted, but maybe after.
Yeah, I said I have a question, but
oh, okay. Sorry, I didn't hear that.
Yep.
Yeah. So when you fuse two codes together by projecting with a cup, which I guess that was an example of that you had. Yeah. This. How do you know that the resulting encoder is still an isometry?
I kind of don't know. I just know that the encoder will be a valid encoder as long as the adjacency matrix between the input node and the output node is full rank. It means that we cannot encode two different states into the same logical state. So when we perform this kind of fusing, as we have seen earlier, almost all the encoder diagram is a stabilizer code encoder diagram, as long as the adjacency matrix is full rank.
Yeah, so it's
from the graph code.
Yeah, so
I was thinking if you take the trivial graph code, just a single qubit to a single qubit, and then you take two of them and you connect them together like this, you get like a 2-to-0 code, and then it's not an isometry anymore. But so, and I think those are still full rank.
Kind of no, didn't get. It's not rank.
Yeah, so if you take just a 1-to-1 code, like you encode one logical qubit into one physical qubit, so there's no error correction.
Okay.
And then if you have two of them and you connect together with the only way you can connect them, then you have 0 qubits left.
Yeah. Then we remove the interior node, it will become the encode 1 qubit into 1 qubit, right? It's the same as the original encoder. Maybe can you like draw the diagram like?
Oh yeah, I guess I can. Yeah, so you have your 1 qubit, your 1 logical, and then you connect it like this with your 1 output, and then you have another copy of this thing.
Yep.
And then you need to connect them up in the only way you can, which is to put a cup here. And then it is a 2-to-0 code. So then it's no longer an isometry.
Yeah.
I guess I'm just trying to say to Alex, like it won't always be an isometry, is I think what the answer is. That it has to be something special about the graph that makes it be an isometry.
Yeah.
Yeah, I mean, if you're saying that in the examples that you've done that you do get a full rank matrix, then that seems plausible. But I don't think there's anything to guarantee that it would always be for any arbitrary fusing of it.
I guess so. We are always choosing the absolutely maximal entangled state to preserve the isometry, the Pentagon stabilizer code. So it's kind of like the building block. Arbitrary stabilizer is not allowed in this setting. So it's kind of like through the tensor network contraction approach, they also have some kind of criterion to make sure the concatenated or the fusing stabilizer is a isometry.
Thanks.
Yeah. Right. Sarah, do you want to ask a question?
Yes, thank you for the talk. I wonder, you just mentioned that when we do the code concatenation, you have an upper bound for the code distance that is given by the two concatenated code. Are you able to use an efficient way to find the code distance after you perform this kind of Bell state projection? Like, do you have any like method to determine the exact code distance instead of the upper bound of the code distance?
Essentially, it's reduced to the stabilizer code. You kind of find the logical operators and you find the one with minimal weight.
So it would still be brute force?
Yeah. It won't be easier than the stabilizer code when you're searching for the code distance.
I see. Thank you.
Yeah.
Hi again. This is a different Alex from Alex's computer. I was wondering, because a lot of this is about simplifying encoders.
Yeah.
I was wondering what is the motivation behind trying to get very small encoders. I'm asking this because in the surface code, for example, you don't actually use data by preparing a state and then passing it through an encoder. You instead have a handful of easy to prepare states like the 0 state and so on, and then you do gates in various ways on logical after post encoding. So so simplifying What's the purpose of simplifying the encoders? Why do you want to have smaller ZX diagrams for them?
It's kind of built on the stabilized graphcode nature. Oh, sorry. I want to move back this. Wait a second. Yeah. It's kind of originated from the essence of the graph code. So when the arrow acting on this kind of graph codes is acting like something classical, the arrow will be like some classical string for the code words. So under this kind of graph code framework, many things can be kind of easier to analyze. That's kind of the motivation why we simplify this into the graphical encoder diagram, because the code space with that is local Clifford equivalent will have the same distance, and we use this graphcode encoder diagram kind of easier for you to analyze the code using some technique for the classical code.
Yeah, thanks.
Yep.
Is it also useful? Does it help in any way trying to get out a system of measurements for decoding? So I mean, obviously you can just take the adjoint, but I mean, like doing non-destructive measurements. Is there any relevance to that here, or is this completely irrelevant?
No, I think first the logical operator for the general graph code is kind of hard to get. You can get the logical X, you can get the logical Z, but the logical hardware is still hard to find. So it's kind of not the nice way to really implementing the quantum error question. It's not even as good as the Steam code, where the logical hardware is transversal. So it's more like a framework for the analyze of the quantum error correcting code, but I don't think it's the best way, except for the holographic code. I think there is still some experimentalists is interested in implement the holographic code, but general graph code is not kind of like the best way to go. So beyond the graph code, there's something called code word stabilized code. It's kind of the same, except that the code words are now not linear, and there's some even better quantum error correcting codes for this kind of framework, but there's no efficient decoding algorithm for this kind of codes. So you have nice codes, but it's not like the best way to go.
Thank you.
Yep.
May I ask, when you contract the two diagrams, have you observed if anything has changed to the transversal logical gate set? So before you contract the codes and after you contract the codes?
Yeah. Oh, I try some like deliberately constructed the encoder diagram. It's possible to induce some strange Clifford in the input nodes, but there's also kind of approach to remove this kind of edge between the input nodes, but it will also transform the graph of the output nodes. I kind of trying to find a systematic way to remove all this Clifford prior to the encoding, but no result yet.
So does this mean before the contraction you have transversal logical Clifford, and after that you have like different?
We have transversal Pauli X and Pauli Z, but we don't have transversal hardware, not even the control node of control Z.
Oh.
Yep.
So maybe Mr. I know that for CSS codes, when they have a transversal Hadamard, if and only if they are self-dual, is there an equally nice characterization of when a graph code is transversal Hadamard?
That's kind of, I'm trying to looking forward. No, I just kind of not figuring out. As you can see over here, the Steam code is kind of a graph code, right? It's local Clifford to equivalent to the graph code, except there's some Hadamard on these 3, 4 qubits. I kind of cannot distinguish this encoder into with other graph codes. I don't know why this kind of graph will result in a transversal Hadamard. There may be some like intrinsic property of the graph.
Right, thank you.
Yeah.
We've been talking for about an hour. I don't know if you have to maybe run and go to the next thing.
No, I can stay.
Okay. Well, I'll see if there are any more questions. We've had quite a few already.
I have a question. Well, since Alex is here, and like Alex proposed the normal form for the CSS code. I'm curious how this graph-like diagram normal form, or like this representation, is related to the phase-free ZX diagram normal form, or they're two different things. They're not related.
I kind of don't know the phase-free diagram normal form. I don't know the phase-free diagram normal form, how it looks like.
So it's like a Tanner graph, but basically you have a bipartite graph, and then you have the checks on the left, and then you have the physical qubit on the right.
Okay. So there's some interior node for it.
And there's no interior node. It's just like two bipartite, like two partition of the graph. And then you have logical operator, and then this logical the X-type stabilizer, and then the X-type stabilizer has the same connectivity as in the Tanner graph, which is the syndrome check, and the logical operator has a connectivity based on the support of that logical operation.
I haven't thought about it.
So these codes are generalized CSS, which means that you won't get this phase-free encoder. But they have the same sort of structure where on the left-hand side you have these logical qubits, and on the right-hand side you have the output physical qubits. But I think that there's a paper by Peter Shore and somebody else, Kesson, who did a thing about encoders, ZX diagrams for stabilizer codes as encoders. So they'll probably look a lot closer to those than they will the phase-free diagrams.
Yeah, they actually just kind of just remove the requirements, kind of like you don't allow to have any Hadamard edge between the input nodes, or more generally, there are no local Clifford operation acting on the input nodes. They defined a canonical form of the encoder, but the transformation is just to say that every encoder can be transformed to its canonical form with some unitary. That's kind of their results. And
yeah, so one thing that I saw that they could represent, but not the ZX normal form, is that let's say if we are still working with the CSS code, and let's say we're working with the 422 code. So 422 code has two logical qubits. This means we have X1 bar, X2 bar, Z1 bar, and Z2 bar. So in the phase-free ZX diagram, or like in Alex normal form, we assume that the logical X is implemented entirely by XX, and logical Z is implemented entirely by ZZ. And then we have the ZX normal form. But we could also switch the label by letting X1 bar be as it is, but let X2 bar be Z1, Z3. So we can still have the definition of two, like X1 bar anti-commute with Z1 bar, but it commute with all the other logical operators. It's still like a valid logical operator set. So I'm not sure if this could be represented by the ZX normal form, but in the Kazan's canonical form, this can be represented. So I wonder if we could say Kazan's normal form is more general than the ZX normal form. Does my description make sense?
Yeah, so
Interesting in the canonical form. Is there some link for the paper or?
I'll put the link in the chat.
Yeah. So during our simplification procedure, we just kind of get a lot of equivalent encoder form. We just
May I write something on the screen?
Yeah.
Okay, so 422 code X1 bar is implemented by X1, X2. And then Z1 bar is implemented by Z1, Z3. And then X2 bar is implemented by X1, X3. And then Z2 bar is implemented by Z1, Z2. But equivalently, we can define like a logical operator set as this, but just put this like here. And this.
Sarah, are you writing? We don't see anything.
Oh, I'm writing. Can you see it?
Yeah.
Yeah.
Oh, yeah, now we can see it.
Yeah. So I was just wondering, can like the normal form that you presented also like related to Kazan's normal, or like the ZX diagram that you presented related to Kazan's normal form. Maybe we could say it's more general because it deals with the bottom case.
So I don't know. For
Maybe I wrote them.
so for the standard encoder of the
Oh, this
graphcode,
is Z1, Z2.
the logical Z.
Not sure if this is what you wrote, Sarah, because X1 and Z1 on the bottom case don't anti-commute.
Oh, sorry, like the X2 bar should be, sorry, it should be X1, X3. Actually, hang on. It should be Z1, Z2. X2 bar should be implemented by Z1, Z2.
Okay.
Oh yeah, I see what you, yeah.
So the way that like I found could generalize Alex normal form is just put the Hadamard gate on the logical operator X2, like, you know, that is connected to the physical qubit. Then that looks very similar to Kazan's normal form, but that is just one fix. But I'm not sure if
So I think I lost the thread a bit. Is the underlying question that can graph code represent any stabilizer code? Is that
Yeah.
sort of the underlying thing?
Yeah, graphical can represent arbitrary symmetrical.
I was thinking
But isn't
if
this if you
graphical-
take any ZX diagram, any Clifford ZX diagram, and you reduce to the GSLC normal form, this is like a graph state with local Cliffords, which is like a graph code with local Cliffords, right?
Yeah. But I'm kind of don't know what the canonical form of this encoder. We prefer to remove the prior to the encoding. But we also want to preserve the symmetry in the output nodes. It's kind of strange because sorry.
I guess my question is, so now we have the graph-like diagram induced representation of encoder, and we also have this ZX normal form. I was thinking about what are the connections between them? Like, does one imply the other, or there are two different representation of the Clifford encoder?
I don't know.
Can I make a comment?
Yeah.
I think there is some relation between both of them, because if you see what you're calling like the normal form for phase-free ZX diagrams can be regarded as performing a Gaussian elimination on the stabilizer tableau of only, say, X stabilizers or something, or only Z stabilizers. And the AP normal form can also be regarded as a kind of row-reduced normal form, but for more general stabilizers, which is not as nice. So I think maybe that's a connection, that they're both correspond to doing to row reducing the stabilizer tableau in some sense. That's my comment.
Yes. In some sense, the graph code is just to perform the Gaussian elimination of the tableau form of the stabilizer. We want the X part to be the identity. And the Z part is the adjacency matrix of the graph. And then
What if you have a mix of X and Z?
but when you
You're in CSS code
no,
scheme, right?
graph code. But when you consider the word operators, actually the stabilizer of the graph code need to remove some of the stabilizer of the graph, because you are expanding the code space. So depending on the code operator, the Z acting on which qubits, the stabilizer of the graph states needs to remove some corresponding nodes of the stabilizer. So suppose my word operator is the Z1, then I have a triangle graph. Therefore, the X1, Z2, Z3 should be removed from the generator of the graph code now. It's kind of and you update. You kind of like the X part of the graph code is pretty close to the identity.
The reason why the CSS code normal form is so simple is because you literally can fully row reduce the matrix, but if you have stabilizers that are both Z and X stabilizers, not only say Z stabilizers, then the row reduction becomes complicated, as Zipeng was saying.
Yep.
Right, but what if you have the case that we just discussed, like when your logical operator are relabeled? So like previous, like you basically just no longer just have the purely X implemented logical X. You have like Z implemented logical X.
Yeah.
Then can you still do the row reduction?
I'm not sure is it what you are looking for.
Because if we look at the 422 code, like the one that we are used to is a simple case where logical X is implemented by just X operators. But what if it's logical X is implemented by Z operators? That's also possible. Then can we still perform the row reduction?
Some conclusion kind of maybe related to your. So when we choose the Clifford operation, the CL equals to the identity, the logical Z, the logical X actually is the Z operators, right? But when we like kind of change the basis using the hardware, the X now turns into the Z, and the Z, the original. I have said that the X is the Z code operators, but the Z operator actually is X, and the left tabular is X. It's S1, and the Z part is the adjacency nodes of that qubit, and we choose the top K nodes.
Wait, but this is for the change of basis for all logical operators. But what if just one logical operator is implemented by the Z?
Oh, that's kind of I'm looking for. I find out. I know how to change when we perform kind of basis change in the encoding space. Actually, like we change the X to the Z. We are performing Hadamard on the top K qubits. We have some logical gates. If we perform the Clifford operation to change the basis for the top K qubit, if we have the logical implementation of the Clifford gates in the logical qubits, then the new logical gate will be the logical Clifford acting on the original logical gates, right? It's kind of like, so it's like your X bar, Z bar should be transformed by the H bar. X bar, Z bar should be transformed by the H bar. But I just can't find the H bar in general.
Oh, I see. Okay. That's very helpful. Thank you. I think now I understand what you're talking about the change of basis.
Yeah, and it's kind of strange when you perform the basis change for the hardware. It's very strange. The logical X and the logical Z will interchange, but as I have mentioned, the X operator now is S and the Z to the neighbors. When you perform the basis change, it will become Z and the X to the neighbors.
And if you have multiple logical operator, it's like you have logical H only on the one of the logical qubits. Not right. So that explains the relabeling of some logical operators, but some remains unchanged.
No, I just can't find logical hardwares. It's kind of like it's a nice property for some CSS code. It's not to generalize to the graph code.
Mm.
All right. If this discussion is resolved, I think we can call it to an end.
Yeah.
Zipeng, thank you very much for